In this video, we're going to be having a look at how we find what's called the volume of a solid of revolution. So let's describe, first of all, what a solid of revolution is. Suppose we've got a graph of a function, y equals f of x. So there's our graph. Let's pick out two values of x. Let's say x equals a and x equals b, and we've identified points on the curve. Now, let's imagine that we rotate this section of the curve about the x-axis through 360 degrees. So this will come round in a small circle, and this will come round in a big circle. And it will form a solid. And we can sketch it very roughly. There's the front bit, and there's the back bit. And then we'll have the curve looking like that. So we've got this curious sort of vase shape almost that we formed by rotating the curve. Now, given an appropriate curve, let's say it was a semicircle. Let me just draw that curve. Supposing we had a semicircle like that of radius r, so it would cross the x-axis at minus r and the y-axis at r. Now, if we rotated that, we'd get a sphere. And if we got the sphere and we had a way of calculating the volume, then we would know what the volume of a sphere was. Well, most people, most of you watching this, probably already know that the volume is 4/3 pi r cubed. But the question is, where does that come from? How can we actually make that calculation? Similarly, if we had a straight line that went through the origin, like so, if we were to rotate that through 360 degrees, then that would give us a cone. So there's the end, giving us the cone, and that's the reflection in the x-axis. And the volume of a cone, we know, is 1/3 pi r squared h, where r is the radius of the base and h is the height of the cone. So again, where does this volume come from? How can we actually calculate that? So that's what we're going to be having a look at. How can we find these volumes of the solids that we get when we rotate curves about the x-axis through 360 degrees? So let's start off with more or less the same diagram that I began with before. Section of the curve, we'll identify 2 points on the x-axis, x equals a, x equals b. We'll draw in the ordinates, and we'll say we're going to rotate this piece of curve between these two limits through 360 degrees. Now, let's have a look at what happens at a general point on the curve at x on the x-axis. Now, when we rotate that, this ordinate will come round and make a circle. Let's move on a small distance, delta x, a small positive increase in x. And let's again identify the ordinate going up to the curve. Now, when we rotate these two together, there isn't a great deal of difference between this and this. Yes, we could say, well, this is y, because this is the point on the curve y equals f of x, and this is y plus delta y, the increase that results from the increase in delta x. We spin this round and we've almost got a small disk. A small disk whose volume we can calculate. if we think of it as being a cylinder. If we think there's so little difference between y and y plus delta y that effectively we can say, all right, let's say this is a disk as it comes round, it's a circular disk, it's a cylinder in other words, and that the volume of this cylinder will be delta V equals, now the formula for the volume of a cylinder is that it's pi r squared h. Let me put that in inverted commas just to show that it is the formula for a cylinder and not quite what we've got here. So this is going to be pi, and the radius of this disk is y, so that's pi y squared, and its height is this thickness delta x. So if we want the volume of the whole of the solid, we need to add up all of these little bits. So we want to add up all of those little bits of volume. And we want to add them up from x equals a through to x equals b. So this will be x equals a to x equals b, and we want to put this in instead of delta b. So that's pi y squared delta x. Now, what we need is a process whereby we don't actually have to do this summation. And in the video integration of summation, what we saw is that when we have a sum like this, if we take the limit as this delta x, this small positive increment in x tends to 0, if we take that limit, then this becomes an integral. So therefore, I'm going to take the limit. So let's write this down. We want v is equal to the limit as delta x tends to 0 of this sum x equals a to x equals b of pi y squared delta x. And the notation that we have for this, as we see in the video integration as summation, is the integral from a to b of pi y squared dx. And that's the formula that will give us the volume of the solid of revolution when we rotate the curve y equals f of x that's contained between the ordinates x equals a and x equals b. Now, let's use this formula in an example. The example I'm going to take is the sphere. In other words, we're going to rotate a semicircle about the x-axis. So I'll draw the semicircle first and then put in the x and y axes. So there's y and x. It's a semicircle, so its radius we'll take to be r. And what's the equation of that curve? Well, that will be y equals the square root of r squared minus x squared. So, this is our equation for y. The volume of the sphere that we get when we rotate this semicircle through 360 degrees is the integral from a to b of pi y squared dx. And now let's identify what the a and the b and the y squared are. So the a is minus r, and the b is r, pi y squared. So we need to square this. So that's the square root of r squared minus x squared, and we need to square it, integrated with respect to x. So we take the integral between minus r and r of pi. We do this squaring, and that's r squared minus x squared, integrated with respect to x. So now we need to look at this integral, and we need to work it out. Turn the page, and we'll write it down again at the top of the page. And one of the things I am going to do is I'm going to take the pi out from inside the integration sign. This is because the pi is a constant, and I don't want it to get in the way of being able to do this integral. I don't want it to be a distraction, because I know it's a constant, I know it's multiplying everything there, so I'm going to take it outside the integral so that it doesn't get in my way, it doesn't confuse what's going to happen. So that's pi, and now let's have a look at the integration. R squared is just a constant, so when we integrate it, we get r squared x. Minus, because we've got minus there, and now we integrate x squared, so that's add 1 to the index, x cubed, and divide by the new index. And now we need to evaluate this integral between the two limits, minus r and r. Equals, so I'll put the pi outside, and now I need to substitute these limits in turn. So let me set up a big bracket, and we'll put in r. So I have r squared times by x, and that gives me r cubed, because x is equal to r. Minus, now I've got x cubed, so that's going to be, when x equals r cubed over 3. Close the bracket, minus, and open another square bracket, and this time we're putting minus r in. So we have r squared times by x, which is minus r, and that gives us minus r cubed. Minus, and now I've got x cubed over 3, and this time x is minus r, so that's minus r cubed over 3. Close the square bracket and close the big bracket. Equals pi, big bracket. Now, let's work out this one. We've r cubed, take away r cubed over 3, so that's r cubed minus a third of r cubed leaves us with 2/3 of r cubed. Minus, that's that minus sign. Now let's have a look at this. We've minus r cubed, minus, and then I've got r minus r cubed. Now a minus sign multiplied by itself 3 times gives us minus. With that minus gives us a plus. So I have minus r cubed plus r cubed over 3, which gives me minus 2/3 of r cubed. So that bit there in the round brackets is exactly the same as that bit there in the square brackets. And let's close off the curly brackets. And now I have a minus, and a minus gives me a plus. We can just get the answer in here. Will be 2/3 r cubed plus 2/3 r cubed, so that'll be 4/3, and let's put the pi in, r cubed. And that's the volume of the sphere that we started off with. So we've been able to show by using this calculus that the volume of a sphere is 4/3 pi r cubed. The other example that we mentioned at the very beginning was a cone. So again, let's have a look at finding the volume of a cone. So we take a straight line that goes through the origin. We'll identify the x values as going from 0 to h, so that h is the height of the cone, and we'll look at the base radius of the cone, which is r. And then when we rotate this line around the x-axis through 360 degrees, we will get a cone. Now, what's the equation of this line? Well, it's a straight line and it goes through the origin. So it must be y equals mx, where m is the gradient. What is the gradient of the line? Well, the gradient of the line is defined to be the tangent of the angle that the line makes with the x-axis, theta. So m equals tan theta. But we can see that we have a right-angled triangle here. The opposite side to the angle is r, and the adjacent side to the angle is h. And so tan theta, which is opposite over adjacent, is r over h. So this means that the equation of our line is y equals r over h times by x. So now we've established the equation of the line, we're now in a position to be able to rotate it about the x-axis. So let's again write down our formula for the volume of the cone that we're going to get. V equals the integral from a to b, those are our x values, remember, of pi y squared dx. And let's now identify all of these pieces. A is the lower value of x, and that's at 0, the origin. So x is 0. B is the higher value of x, so that's h there. Pi. And now we want y squared, and we established that y was equal to r over h times by x. So that's r over h times by x, and we have to square it. And that is to be integrated with respect to x. Do remember to square the y. It's a very common error just to put in y and then integrate it without squaring first. Okay, turn over the page, and as we do so, we're going to write down what we've got here to integrate. So our volume is equal to, and again I'm going to take the pi outside the integration sign so that I don't get confused by it. It doesn't get in the way of the integration. The limits are from 0 to h, and I need to square the y. And if we just look back, we'll see that the y was rx over h. So if I square it, it will be r squared x squared over h squared. So let's do that. R squared x squared over h squared to be integrated with respect to x. So pi, square bracket, r squared over h squared, that's just a constant, and x squared. We integrate the x squared, add 1 to the index, that's x cubed, and divide by the new index. So we divide by 3. And this is to be evaluated between 0 and h. Equals pi. Put the h in first, so with r squared over h squared times by h cubed over 3. So there's our first bracket, minus, and the second one, when we put 0 in, r squared over h squared times by 0 over 3. And of course that means this end bracket is 0. So we only need to look at this. We can see that we have an h squared here, which will cancel with the h cubed there, leaving us with h. And so we'll have 1/3 pi r squared h. And that's the standard formula for the volume of a cone. Okay, we've had a look at 2 fairly standard formulae that we knew already, and we've seen how we can calculate them using calculus. But of course, these aren't general curves. They were fairly specific cases. So this time, let's have a look at a slightly different question. This is a question that occurs in many textbooks, or of a style that occurs in many textbooks. Take the the curve y equals x squared minus 1 and find the volume of the solid of revolution when the area contained by the curve and the x-axis is rotated about the x-axis through 360 degrees. So here we've got our curve, and we want the volume of solid of revolution when the area contained by the curve and the x-axis. That suggests that we really need to look at a picture of this curve. We really need to sort out where it is in respect of the x-axis. So let's have a look. We've got y equals x squared minus 1. We want to have a little sketch of this curve. We want to know what it's doing. Y equals x squared minus 1. Well, one of the things that will be useful to know is where does it actually cross the x-axis? So in order to do that, on the x-axis, we know that y equals 0. So let's write that down. Y is 0, so x squared minus 1 must be 0, where it crosses the x-axis. So we can factorise this, and this is x squared minus 1, so it's the difference of two squares. So we'll factorise as x minus 1 and x plus 1 equals 0. Now this is a quadratic equation that we factorised into two separate factors. So if the two factors multiplied together give 0, then one of them is 0, or the other one is 0, or they're both 0. And this tells us that then x equals 1 or x equals minus 1. So we know that the curve goes through there and through there. What else do we know about this? Well, what if we set x is equal to 0? What if we investigate what happens when x is 0? Well, straight away we can see when x is 0, y is equal to minus 1. So the curve's down there. So we can tell now that the curve must look something like that. And this is the area that is trapped between the x-axis and the curve. So this is the area that is going to be rotated through 360 degrees, and that we have to find the volume of that solid of revolution. So now we've got a picture and we know what we're doing. We're in a position to start the calculation. So we begin with v equals the integral from a to b of pi y squared dx equals. First of all, let's identify the limits of integration. Well, this was where the curve passed through the x-axis. So the limits of integration are minus 1 and 1, the values of x, where the curve cuts the x-axis. Pi and y squared, well, let's just be careful here. We know that y is x squared minus 1. So we can write that in. X squared minus 1, and we remember to square it. Integrated with respect to x. Now we've got to square out this bracket. We've got to multiply it out. So integral of pi, notice I'm moving the pi outside the integration sign again. And I want this squared. So let me do it here in full so we can see where all the terms come from. That's what the square means. Multiply the bracket by itself. So with x squared times by x squared, that gives us x to the power 4. With x squared times by minus 1, gives us minus x squared. With minus 1 times by x squared gives us minus x squared. And with minus 1 times by minus 1 gives us plus 1. And this middle term, we have minus x squared, so with x to the 4th minus 2x squared plus 1. So this is y squared, which we can write in here. X to the 4th minus 2x squared plus 1 dx. Notice that is important to make sure you get this square right. And so it's a good idea to do it at one side, to write it out in full, just to make sure you get it right. Okay, I'll turn over the page and we'll go through this integration. So our volume V equals pi times the integral from minus 1 to 1, x to the 4th minus 2x squared plus 1 with respect to x equals pi. Now we'll do the integration. The integral of x to the 4th is x to the 5th, adding 1 to the index and dividing by the new index. So we have x to the 5th over 5 minus 2. X squared, when we integrate it, is x cubed over 3, adding 1 to the index and dividing by the new index, plus, and the integral of 1 is just x. And this is between minus 1 and 1. Let's substitute in the limits. Take the 1 and we put it in first. That gives us a 5th minus 2/3, because all of these powers of x are just 1, plus 1 minus, now we have to be a bit more careful this time because we've got minus 1. So when we put minus 1 in, minus 1 to the 5th is minus 1 over 5 minus a 5th. Minus 2/3 of, now x is cubed, so it's minus 1 cubed, and that is minus 1. And then plus, and we're putting minus 1 in, minus 1 there. Equals pi. I just need to squeeze in a bracket, just to close that bracket. Now let's work out each of these two brackets. Now we need some knowledge of fractions to be able to do this, and by the looks of it we're going to need a common denominator. So let's make them all over 15. 15 because 15 is 5 times by 3, and both 5 and 3 will divide exactly into 15. So 5 into 15 goes 3, so 1/5 is the same as 3/15. 3 into 15 goes 5, and so 5 times by 2 is 10. 10/15 is the same as 2/3. And 1 is a whole 1, so it must be 15/15. Minus. Now, going to convert these into 15ths as well, but we need to be a bit careful about the signs while we're doing it. So this is minus a 5th, so in terms of 15ths it must be minus 3/15. Now I have a minus and a minus there, that will make that a plus, and so that's going to be plus 10/15. And then here I've got plus and a minus, so that's going to be a minus, and it will be 15 fifteenths. Equals pi times, now let's have a look at these. We've 3 fifteenths take away 10 fifteenths plus 15 fifteenths. So the 3 and the 15 give us 18, take away 10, that's 8 fifteenths. So that's got that one sorted. Minus, now let's have a look at this. We've minus 3 fifteenths, minus 15 fifteenths, so that's minus 18 fifteenths, plus 10 of them, that gives us minus 8 fifteenths. So minus 8 fifteenths. And we can just finish this calculation off now, because with 8 fifteenths minus 8 fifteenths gives us 16 fifteenths, and pi times by pi. So there's our answer, and that's our calculation. There is one more thing that we just need to have a quick look at. If we can rotate a curve about the x-axis, spinning it round here through 360 degrees, there's actually no reason why we shouldn't rotate a curve about the y-axis, spinning it around the y-axis. So let's say we did that between the values of y, which are y equals c, and y equals d. Well, there really is no difference between spinning it around the y-axis and spinning it around the x-axis. The way that we calculate it is going to be the same, except because we've spun it around the y-axis instead of the x-axis, the x's and y's are going to interchange. And so we end up here with the idea that the volume in this case is from y equals c to y equals d of pi x squared dy. And in the same way as we had expressions for y in terms of x, in order to do this, we would have to have expressions for x in terms of y. And then we can integrate with respect to y, substitute in the values of y, and obtain the volumes. So that's volumes of solids of revolution.